In this video, I want to have a look at parabolas, tangents, and focal chords. So we're going to have a look at the parabola x squared equals 4ay, and we're going to look at 2 points on that parabola, P and Q. So in our earlier video on chords, we know that the equation of the chord PQ is y minus a half P plus Q x plus a P Q equals 0. Now that's for any chord PQ, but what we want to look at specifically in this video is focal chords. So a chord becomes a focal chord if it passes through the focus of the parabola. So if we have this parabola here, it's concave up, and it's got a focal length of a, then its focus has coordinates 0, a. So if its coordinates are 0, a, and we know that this chord passes through that point, then we can substitute those values in for our x and y because we know that that point satisfies the equation. So we're going to substitute a in for y and 0 in for x. So we're going to have a minus a half P plus Q times 0 plus a P Q equals 0. Now that 0 here is going to eliminate that entire middle term. So we're going to have a plus a P Q equals 0. And if we rearrange that, we can have a P Q equals minus a, or P Q equals minus 1 if we divide through by a. Now what that actually means, if we have a think back to our video on tangents, and we're looking at tangents at the point P and Q, we found that at the point P, if we drew a tangent, that tangent had gradient lowercase p. And if we drew a tangent at the point Q, it had gradient q. So this lowercase p and q, they're the gradients of our tangents from these points. So if those tangents multiply to give minus 1, what that means is that those tangents are perpendicular. So that's our first important piece of information, is that those tangents are perpendicular. But there is something else as well. Now, if we know that that's perpendicular, we can use that when we're finding where those tangents intersect. So again, from our video on tangents, we know that if we've got two tangents from a parabola, they're going to intersect, or their point of intersection is going to have coordinates a outside of P plus Q, a, P, Q. Now, if we know, because we've already figured it out, because it's going through the focus, we know that PQ is going to equal minus 1. So this is going to become a outside of P plus Q minus a. Now, what's interesting here is that y coordinate has become minus a. Now, again, if we're looking at this parabola, we know that it's a concave up parabola. We know that it has a focus at 0a, and we know that it has a directrix with equation y equals minus a. And the y coordinate here is minus a. So what that's telling us is that if PQ is a focal chord, then the tangents from P and Q are going to intersect at right angles, and they're going to intersect on the directrix. So we're going to write all of that down. All right, let's have a look at an example. So we've got the points P, 2 minus a half, and Q minus 8 lie on the parabola x squared equals minus 8y. Part A asks us to find the equation of PQ. Now, because this is in our standard form, I'm not going to just plug numbers into that formula. What I'm going to do is I'm going to go through and derive it again. So I'm going to start off, so this is for part A, with that y minus y1 equals m outside of x minus x1. So to find m, we're going to go y2 minus y1 over x2 minus x1. So minus 8 minus a half over minus 8 minus 2. And that will all simplify down to 3/4. And then we can substitute in here. We could use either P or Q, doesn't really matter. So let's go y plus a half equals 3 over 4 outside of x minus 2. Now I'm going to go through and multiply everything by 4 to get rid of that. So I'm going to have 4y plus 2, and I'm going to expand my 3 here. It's equal to 3x minus 6. And if I pull all of that onto one side of the equals sign, I'm going to have 3x minus 4y minus 8 is equal to 0. So that's part A, that's the equation of the line PQ. Part B asks us to show that PQ is a focal chord. So that means that we know it's a chord, we need to prove that it passes through the focus. So to be able to do that, we need to know what the focus of our parabola is. So this is going to be a concave down parabola. So to find the focal length, and it's got the vertex at the origin. To find the focal length, we know that 4a is going to be equal to 8, the coefficient of y, which means that a is just equal to 2. So that means our focus has coordinates 0, minus 2. So to prove that it's a focal chord, we need to prove that that point satisfies the equation that we got in part 1. So to do that, it was, just to remind myself, it was 3x minus 4y minus 8 equals 0. So if we have a look at the left-hand side of that equation and we substitute in our x and our y, we're going to have 3 times 0 minus 4 times minus 2 minus 8. So that just gives us 0 minus 4 times minus 2 will give us 8, and we've got our minus 8 on the end, which equals 0, and that is equal to our right-hand side. And therefore, that means because the focus, the coordinates of the focus do satisfy the equation of our chord, that means that the chord does pass through the focus, and therefore it is a focal chord. Alright, so that's A and B. Let's have a look at C. For part C, there's two different things that we need to prove. We need to prove that the tangents at P and Q intersect at right angles, and we also need to prove that their point of intersection is on the directrix. So to start off, let's find the equations of the tangent at P and the tangent at Q. So from our video on tangents, we know that a tangent is going to have coordinates equation x, x1 equals 2a outside of y plus y1. So at P, the tangent is going to have equation x, x1, so x1 was 2. So it'll have equation 2x equals 2a. And like we figured out before, from this equation, our a is 2. So that's going to become a 4 outside of y minus a half. Now if we rearrange this to make y the subject, I'm going to divide both sides by 2 first. So I'm going to have x equals 2 outside of y minus a half, which means that x is going to equal 2y minus 1. Making y the subject, 2y is equal to x plus 1, which means that y is equal to a half x plus a half. So that means the gradient of the tangent at P, so let's call it m1, is equal to a half. Now if we go through and do the same thing for Q, so at Q we're going to have equation x, x1, so minus 8x, equals 2a, which again, the a was still 4 because it's all still from this same parabola, so we'll have 4 outside of y minus 8. So I'm going to divide everything by 4, and that'll give me a 2 there. So minus 2x equals y minus 8. So we'll have y equals minus 2x plus 8, which means that my gradient of the tangent at Q is minus 2. Now looking at that, we can go m1 times m2 would be minus a half times 2, which will give us minus 1. So therefore, those two tangents are perpendicular. Right, so that's proved the first part. It proved that they do meet at right angles, but we also need to prove that they intersect on the directrix. So to do that, we're going to solve these two equations that we have simultaneously. So I'm going to call this one here equation 1, and I'm going to call this one here equation 2. Now I'm going to sub 1 into 2, so I'm going to have a half x plus a half equals minus 2x plus 8. I'm going to go through and multiply everything by 2. So I'll have x plus 1 equals minus 4x plus 8. Rearranging that, I'll get 5x. Oh, sorry, hang on. That should have been a 16, not an 8. Because I times them by 2. Rearranging it all, I end up with 5x equals 15, which means that x is equal to 3. So that's the x coordinate, but that doesn't help us yet. We also need to find the y coordinate. So I'm going to sub that. I should have written 1 into 2 here. I'm going to sub x equals 3 into equation 2. Could have done it into 1, doesn't really matter. and that's going to give me y equals minus 2 times 3 plus 8, which would be minus 6 plus 8, which is equal to 2. So that means that the coordinates of the point of intersection are 3, 2. Now, we already figured out that the focal length of this was the focal length A was 2. We know that it's a concave down parabola, that its focus was 0, minus 2, and its directrix would then have to be y equals 2. So because our point of intersection has coordinates of 2, that's proof that this point of intersection lies on the directrix. Alright, so that's proved that it's perpendicular and it lies on the directrix. I want to have a look at one more property of focal chords and parabolas. If we have a tangent at a point P on a parabola, it's going to be equally inclined to the axis of the parabola and the focal chord through P. So that doesn't make a whole lot of sense without a diagram, but let's have a look at what it means. So if we pick a point here and call it P, if we draw a tangent to that curve, to the parabola through P, looks like that. Now we know that this concave up parabola has its axis of symmetry straight down that y-axis. So the angle that the tangent is inclined to the axis of symmetry of the parabola is this angle in here. Let's call that theta. Now the other part of that is it's equally inclined to the focal chord through P. So if our focus of our parabola is here, if we draw the focal chord, now I've only drawn part of the focal chord, the chord should go all the way over to the other side, but if we just draw that part, then this angle in here would also be theta. Now we're going to go through and prove that. So to do that, we're going to add a bit more detail to this diagram. So we're going to say our P has coordinates 2AP, AP squared. We're going to call this S our focus, and it has coordinates 0, A. We're going to draw in our directrix, which would be somewhere along here, which is going to have equation y equals minus A. We're going to call this point down here Q. We're going to draw a line straight down from P, a line straight down here. We're going to call that point where it meets the directrix, we're going to call that R. And we're going to call this x-intercept of that straight line T. So that looking pretty messy, but it's all going to come out fairly nicely in the end. So if we have a look at the length SP there, then we know that SP is going to have to equal PR. Now that's from the definition of a parabola. We know that the parabola is the locus of all points that are equidistant from the focus and the directrix. So from the point P, the distance from the point to the focus has to be the same as the distance from the point to the directrix. So SP has to equal SR. Now if we look at that length PR, that's going to be the distance PT plus the distance TR. So that distance PT, that's just going to be the y-coordinate of P, which is AP squared. And the distance TR, well, we know that R lies on the directrix, which has y-coordinate minus A. So that distance there has to be A units. So that means that the distance SP, so from the focus to the point, is AP squared plus A. Now let's leave that for a little while now. Let's find the distance SQ. So to find that distance, we need to know the coordinates of Q. So we know that the tangent through P is going to have equation y equals px minus AP squared. Now Q is the point where that where that tangent crosses the y-axis, so it's going to have x-coordinate of 0. So at Q, x is equal to 0, which means that we're going to have a y-coordinate of minus AP squared for Q. So the distance SQ is going to be the distance SO, if we call O the origin, so SO plus OQ. So the distance SO, because the focus has coordinates 0A, the distance from the origin to the focus is just going to be A. And the distance from the origin all the way down to Q, well, we've just found out that the y-coordinate of Q is minus AP squared, which means the distance there is AP squared, which is exactly the same as what we had up here. So what that means is that the distance SP is equal to the distance SQ, which makes the triangle SPQ an isosceles triangle. And that means that this angle here is going to be equal to this angle here because they're base angles of an isosceles triangle. All right, so the last theorem to do with tangents and focal chords.